Okay, so this is the array that we're given, and so we want to compute this thing. So the first thing I do is, this is my array. So the first thing I do is I compute this binary index tree, and it's going to be composed of this array where I'm going to index it from 0. So I'll fill it in. I don't know if I have space over here. Ooh, okay, I'll try to do it over here. I just realized my spacing is really bad. So at the beginning, it's going to be the same values, but we're going to update this and make it compute a bunch of ranges and stuff. Okay, so the first thing we do, one thing that you use when you're going to use this concept, we're going to use this a lot, and -I. So what this does is it extracts the last set bit, and so when we extract the last set bit, we're gonna like do stuff with that. And like, what do I mean by extract the last set bit? Well, like, let's say you have 0, 0, 1, 1, then you invert it, you're gonna get 1, 1, and it's 2's complement, so you add 1, and if you AND these, you're gonna get 0, 0, 0, 1. You get the last set bit, which is this 1. So that's the basic thing. So then, so yeah. So after that, yeah. So after this, here, I don't think too much is going to happen, but yeah. So I'll go over a little bit what I'm gonna want to do, how it's gonna work out. So this is cool, right? So we have the 0, 0, 0, 1. But we do want to end up computing this thing. I'm getting a little distracted, but yeah, this extracts the last bit. We're going to do that. So one thing we're going to do is we're going to start iteration. We're going to create like an iteration. We're going to start at I equals 0, or I equal 1, because we're going to 1 index this. Okay, so I equals 1, 1, and then what we're going to do is compute this second index, which is going to be basically extracting the last set bit and adding it, which obviously is going to be 2 here. And then as long as this j is less than the length of our array here, then we can increment our bits. So I would want to increment this one at j based off the value at -1, which is that. So this will be 1. And that's what we do right there. Okay, so I literally just updated this to be 1. Okay, well, then let's continue. So then we iterate, we go to I equals 2, and in this case, if we extract the last set bit, that's a 0, 0, 1, 0, it's here. So if we add that to our current number, that's 2, so it's going to become 4. So here we're going to go to 4, and we're going to take the binary index array at 4, which is 5, and add it to the binary index value at 2, which is 1. So this would be 6. Okay? And then we're going to go to I equals 3. And so if we do this, it's going to j, that's going to be 4. So it's going to add the value at 3 to the value at 6 index, which is 6 right now. We updated it to be 6, but it's going to change here in a minute. So it's 6, but now we're going to add this 3 to it, so it's going to become 9. Okay, so this is now 9. And then we're going to iterate to I equals 4, and so j will be equal to 8, but I think j equal to 8 will be out of range, so whatever. So we go to I equals 5, so j will be 6. So we add up those two, which is 6 plus 1, which is 7. And then we go to I equals 6, which gives me j equals 8, which is out of range. So we go to I equals 7, which gives me j equals 8, which is out of range. So it's just going to be 10. So we change this value to 7. Cool. So this is what my binary index tree looks like. And now let's think about what this is telling me. So this 1 is the prefix sum of -1 to 2. So this here is the range of, oops, I just realized I don't know how to do this. My bad. Okay, so the first value here is this 1 here is a couple of things. So, or we can think about let's think about what this binary index tree is telling me. So the 0 index we don't really worry about. The 0 index is kind of like anything before it. The -1 is kind of like the range 0 to 0, you know? And then the value 1, is kind of like, and I forgot. It's kind of weird because I'm going back and forth between 1 index and 0 index. So let's just keep using the 1 index for right now. So say the value is 1 and 1, and then we go to the next value. This value is 1, right? But this is a summation of 2 and -1. So this is the range of 1 to 2. And then we go to the next one, and this value is actually 3, which is literally just the range of 3, 3. Then we go to the next value, which is, I realize I'm probably going to run out of space, which is the range of, it's this one here, the 9. Well, the 9, we computed, it's -1 plus 2 plus 3 plus 5. So it's literally the range from 1 to 4. And then we compute the range from 5 to 5, and then we compute the range from 5 to 6, and then we compute the range 7 to 7. So these are all the ranges that we've computed. This is literally what our binary index array, which is supposed to represent a tree, is looking like, I guess. Okay, so now we need to figure out something else. Okay, so we figured all of this. The next step really is we've built our binary index tree. And let me make sure. So the next step is basically, how are we going to update this? You know, how are we going to update a value? So I'm going to go over how to update. Okay, so let me get myself some space. Okay. This is enough space for right now. So we're going to do updating. Okay, so let's suppose that we want to update let's suppose we want to update the value at let's say the 3, okay? So let's say we want to update the 3, which is at index 1, 2, 0, 1, 2, we'll update our code to reflect this. So we'll do everything in one index, so it's at 4. So it's at location. Well, in the original array, though, I have to think about in terms of the original array, I guess. So the original array is at index 0. And, yeah, this is the original array. Yeah. So the original array is at index 0. And then, why did I say, what am I talking about? No, the original array is indexed from 0, but the index value that it will have will be 0, 1, 2. Will be 2, and we're going to update it to, let's say, a 5. Okay, so that means that our array is going to change to this. So I'm going to write down my new array. -1, 2, 5. I updated a 5. Okay, and then we have a 5, and then we have a 6, and then we have a 1, and then we have a 10, and then we have our BIT, and we index this from 1. This is 0, -1, 1, 3, 9, 6, 7, 6, 7, and 10. Okay. So how are we going to update this? So I want to update my BIT. I've already updated my array. My array is really easy to update. But to update my BIT, first off, this is index from 1. So we're going to start with I equals 3. We're going to commit it by 1. And then what we'll do is I'll find the increment. So first off, I'm going to keep track of the increment, which is how much it's increased by. So it's increased by 2. That is, the original value was 3. So 5 minus 3 is 2. So we increased the value at the index 2 by a value of 2. Now this is important because we're going to have to use this for update the BIT. So we start at I equals 3. So if we look at I equals 3 in our binary tree, we need to increment it by 2, right? And also realize that the index 3 is 0, 1, 2, 3. It's this 3 right here. And that 3 right there is from range 3 to 3. Which is definitely affected. Yeah, so it's definitely affected by the fact that we incremented this by 1, right? That range is affected. Basically, any range that includes 3, any range that has 3 in interval is going to have to be updated. So here, we start with I equals 3. So the methodology is we're just going to update this by the increment. So we take the bit array, and this will update this to 5. And then the trick is we're going to do I plus or equal to, and we're going to take the I and minus I. So we're going to extract the last set bit and add it. So if we do that, we're going to go to I equals 4, and then we're going to update that value as well. So that value right now is 9, so we're going to increment it by 2, which will give 11. Now let's just think, does this actually make sense? It does, because the next value, this value is range 3 to 3, so it's affected. The next value is range 1 to 4, so it's also going to be affected by if you increment the value at index 3 in terms of the 1 index system. So yeah, so this will be affected, right? There's no arguing there. Now, are 6, 7, 10 going to be affected? Well, they're not. So let's see if this code will work. So after we do use 4, we're going to go to 8 when we use this thing. And the problem with going to 8 is that we're out of range. So okay, so we're done. Okay, so that just updated our BIT. Now the question is, how are we going to compute the sum ranges? That should be the next question. Okay. And I'll do an example. My example will, I guess, be 0, 1, 2, 3. Let's do 2 to 3 maybe. 2 to 3. Okay, so let's set up some space for this. This is how I generate space right now. I don't know, is there a better way to generate space? Okay, it might be enough space. Okay, so let's go back up. Okay. Alright, so far what have we done? So we've started with an original array that's indexed from 0. We've created a binary index array, or a binary index tree represented in an array that's indexed from 1. In that array, it contains values within these certain ranges that are kind of representative of binary numbers. I'll go over that a little more. We use this this bit manipulation here to update. So okay, yeah, so let's see, we use it to actually generate our binary index tree in an array representation. Then we go down here and we're going to update. We update a value in our array, which causes us to also have to update our binary index tree. So the last thing we need to do is we need to compute the sum range. So let's say we compute the sum range from 2. Let's do 1 to 3. Okay, let's say we want to do this. First off, what's the answer? The answer will be 2 plus 3 plus 5, which is 5 plus 3 is 10, so it's, sorry, 5 plus 3 is 8, plus 2 is 10. Okay, so it's going to be 10. So how do we get this? Well, my bad. It's going to be 2 plus 5 plus, it's going to be 12 because we updated. Yeah, because we updated. We're using this updated version. Okay, so what we might do is we might take the sum of 3 minus the sum of 1. Now, the sum of 3 if we think in terms of prefix sum, it would be 11, right? So it's this one here, 0, 1, 2, 3, 4. Notice a problem. That's at index 4 in my binary index tree. So when I take the sum, I need to increment this by 1 to 4. So I basically just add 1 to my end range. But if at the beginning, I don't add 1 to it. Because I actually do want to go back to the 1 position, which is the 1 is right here, right? This is what I do want to subtract the value there, because that value corresponds to this value, and this is not in my range. So we had to do that, and then right, and then what we can do is compute the sum. So what's the sum here? So let's say I is equal to 4. So what we'll do is we're going to increment our result. So our result is going to be equal to, well, it's 11. You know, it kind of makes sense that this is 11. So this is 11, right? And then what we do is we're going to decrement this by I and negative I. So we extract the last set bit and decrement, but this is always going to go to 0 because it's 0, 1, 0, 0. Subtracted by 0, 1, 0, 0, which is 0. Then what about sum 1? So I is equal to 1. The res is negative 1. So if we subtract these, is going to be minus -1, which equals... Where did I go wrong? Where did I go wrong? Why am I getting 10? I'm not getting 10. Whoops. This is 12. Cool. So it equals. It equals. Now I'm going to look back up at this. So here we did the sum range, right? And if we do the sum range of, this is why let's say I did 1 to 0, right? Or sorry, 0 to 1. I mixed it up. So if we do that, we're going to take sum of 2 minus sum of 0. So at 0, that's just 0, you know, it's just 0. That's how we put 0 there, because we're taking this up from the beginning to the 2. And 2 is, or we're going to 1. Sorry, I'm going to 1 by incrementing by 1 to get 2. So if I look at my binary index tree, that corresponds to 1. And so it's equal to 1. Is it true? It is true. -1 plus 2 is 1. So that works there. We could also do something like sum range (3 to 6). This one's kind of interesting. So if we're going to do that, 2 to 6, we're going to take sum my bad. Let's do 3 to 5. So we're going to take sum 6 minus sum 3. Okay, so compute the 6th one. So I is equal to 6. So we get res equals, initially at I equals 6, 0, 1, 2, 3, 4, 5, 6, it's 7. So we get 7, but then this is going to become, if we subtract the last set bit, which is 2, we're going to have 4. So then we subtract that, which is at 4, which is, or we don't subtract, we add it, so that's 11. So we get 18. And then I equals 3. We get res equals 0, 1, 2, 3, 5. And then we decrement this by 1, because the last set bit is 1, so it's going to become 2. And at 2, 0, 1, 2, we have 1. So plus 1, which is 6. So it's 6, which is equal to... well, it is equal to 12. Is this correct? Sum of 3 to 5. 0, 1, 2, 3, 4, 5. Yeah, that's right. 5 plus 6 is 11, plus 1 is 12. Okay, so it works there. Now, kind of we can look at why this worked as well. So look at our ranges up here. So to be able to compute this, what we did really is we computed the range. So at I equals 6, what do we have? We have 0, 1, 2, 3, 4, 5, 6. This is 6 actually. So the 6 is 5 to 6. So we took range 5 to 6 plus, and then we decremented to 4, and 4 I think is range 1 to 4, plus range 1 to 4, which if we're 1 indexing, this is the range from, this is equal to the prefix sum from 1 to 6, which, so I don't know, I think I messed up by 1 indexing it, my bad, but yeah, so this is the whole array to 6, and then you compute this 3, which is going to be range of, let's see, so at 3 is 3 to 3, I guess. So it's 3 to 3, and then you need to add the range at 1 to 2. So you get a total of range of 1 to 3. So you're subtracting the range of 1 to 6 minus the range 1 to 3, which makes sense, right? If you're doing prefix sum arrays. Okay, so now go over a little more why this works. So if I go up to the top here. Alright, last part of this video, and then we're going to get to the code. So I want to show something here, which is a way to see the tree that that I'm going to do. Move this 9 up to, oops, I lost my mouse. Move my 9 up to here, and bring the -1 down here. Bring this 3 down here. Bring this 6 down here. No, oops, -1. Erase. Trying to erase this. So this 3 down here, and I mean, why am I doing this? Because everything on this first row is a range of 1 to 1, 1 to 2, and 1 to 4. So these are all ranges of 1 to x. And I'm so sorry, that's index from 1, that's not index from 0. Oh my gosh, why did I do that? I have to rechange this whole thing. I mean, but yeah, just imagine this is 1, 2, 3, 4. Okay, so this is 4. Because it works with the binary index tree. That's why I did it originally. But and then here, everything down here is range 3 to x. Well, we only have this one, range 3 to 3. And then everything down here we'll do range 5 to x. So we'll do range 5 to x, which is 6 and 1. And then 10 is range 7 to 7, so this one's down here. Now let's look at the binary representation of all of these numbers and how these ranges make sense in terms of binary and why this all works out. So the binary representation of 1 is 0, 0, 0, 1. Binary representation of 2 is 0, 0, 1, 0. The binary representation of 9 is 0, 1, 0, 0. Sorry, the binary representation of the index by 1. That's also why index by 1 is because the binary wouldn't work. And then the 3 is 0, 0, 1, 1. This 6 is at by 5, so it's 0, 1, 0, 1, and this is 0, 1, 1, 0, it's 6, and there's index 7, which is 0, 1, 1, 1. Okay, now check this out. So these are binary representations. So now let's look at how we do an update. So how we do an update is, so remember, when we do update, we increment by the last set bit. We increment by the last set bit. So imagine what we did. So we updated the 3, remember? I think that's what I updated. Is that what I updated? That is what I updated. Yeah, I updated right here. So that's why I updated. So this 3, the last set bit is this 1, right? So we add, sorry, you add 1, so you add the last set bit. If we add the last set bit to this, we're gonna get, well, I mean, what are we gonna get? We add 1 to 3, we get 4. So we go up here, and I'm gonna start changing colors. Oh, my mouse is disappeared on me. Oh boy. Okay, is it back? Okay, it's back. Okay, I'm going to go here, change the color to red, and say I move this way up the tree. I move this way up the tree. This is kind of like the parent, right? We're kind of using binary index. So then this is 0, 0, 1, 1. When we move up the tree like this, you know, then we might try to move up the tree again, but we're just going to get, it's going to go out of range, right? Like there's no other place to move up the tree anymore. Because if you subtract, or sorry, if you add another 1, you're going to get 1, 0, 0. So yeah, you can't. This is for updating, by the way. So it's going to update these two values. And this makes sense, right? Because this value, again, is in range 3, and we're trying to update 3. This value here is including the 3. And if there was a number out here, it would be 1, 0, 0, 0. And if we add this 4, we would go out here, and that would make sense because the number out here would be at range 1 to 8, which does include the range 3. Basically, anything in this row, anything in this second row includes 3, and anything in the first row includes 3 as long as it comes after it, like this. So anything else down here would include it. Okay, so that's how kind of update works. And you kind of see if you were updating the value here, you'd have to go here first, and then it would go up, but there's nothing up here, so there's nothing else within the range if you're updating the 5. This is out of the range. Okay, now what happens when you do sum range? So when we do sum range, instead of adding the last set bit, we subtract the last set bit right here. So if we subtract the last set bit, that means that, let's say we use this example where we did sum range 6 minus sum range 3, right? And this is how we get the result. So we take 6, and 6 is this one, right? Now if we subtract the last set bit, which is this 1 here, we're going to get 4, right? So it's going to go I messed up. We're actually here. My bad, we're actually here. Why did I do that? I started the wrong place, didn't I? Yeah. Yes, I'm supposed to start at I equals 6. Okay, yeah, I equals 6 is actually here. This is the 6 index and the 1 index. Okay, so we subtract 1, and we get, if we subtract 1, we're going to go over here to this value, right? So we're going to do the sum range 5 to 6 plus sum range 5 to 5, and if we subtract from this one, oh, you know what? I messed up again. Okay, when you subtract, my gosh. Okay, so this is 0, 1. Yeah, so when you subtract the last set bit, this last set bit is 2, right? So we have our value 6. 6 minus 2 is 4, so we're going to go to 4. So where is 4 at? 4 is right here. So we go up. So we go up and to the left, kind of backwards. Makes sense because this will have the range 1 to 4, and this value here has the range 5 to 6. So add them together, you get your complete range. Cool. Then what we'll do is this range 3. So what about 3? So if we start at I equals 3, that's 1, 2, 3. That's this one. If we subtract 1, we're going to go up and over here. And this will work as well because this is range 1 to 2. This is range 3 to 3, so that's a range of 1 to 3 total. So yeah, so that's how it works. Now let's actually code it. That'll be the last part. How much time do I have? Ooh. Okay. Okay, so we'll get started on the code. So this is all going to change. First thing is I want to construct the binary tree. So I'm going to create a self-array that I can access later for updating the values in it. Yeah, I do need to do this. Then I'm going to create my binary index array. I'm just going to BIT. And what I'm going to do is I'm going to 0 index it, give it a 0, and plus none, right? That's kind of like what I did at this point. And then iterate through the thing. So I did for I in range, I went from 1 to the length of self.bit, and at each part I computed I extracted the last set bit and added it to the I to be able to find where and what range we're going to find the second part of the range. And then I had to make sure that J was within the range. And then if it was, I would update the BIT at J, and I would increment it based off the value at I. Right, that's what I did. That's what I did right here. So like, I computed, so I did the range -1, and -1 went to 2, and then this went to the 5, and I added them up, and then once I would go to this 3, this went to the 5, and it incremented it again. So I'm incrementing based off the J, the value at the J plus the value at the I. That makes sense. And then update. So for an update, I get the increment. Update the value of the array. So I need to increment everything within the range by this. Okay, so I'll say so we'll move through the self.bit to update the ranges. And so the first one we'll do is one issue here. We have to increment I, because you have to remember the BIT is indexed from 1, and so we padded it with this 0, versus the self.array was not. So we have to increment the I. And then what we'll do is update the values at I based off the increment. It could be negative as well. The increment could be negative. And then update this going to the next value. Okay, and it's sum range. We'll return. So I'm gonna create a function for prefix sums. Prefix sum at J, and remember I incremented it by 1, minus self.prefix sum at I. Okay, so let's compute the prefix sum. So we're given an index. So how does this work? We have a result. Our result is 0. And then what we're going to do is we're going to increment, while I. So we decrement I in this case. So we increment I to update, and we decrement I to get the prefix sum. But first, we're going to do res plus or equal to bit at I, and then we'll do that. And we want to return the result. to test it out. And go over the time complexity of this. So the time complexity of this is the prefix sum is O of log n, because a property of okay, cool, it passed. Yes, and it's pretty fast. So basically the time complexity for this is we're iterating through n here. So this is O of n to initialize. We'll only initialize once, so it's like, okay, that's fine. Every time we update, it's going to be O log n, because we're going to go through the number of bits, and for any number, the number of bits is O log n, whatever the value is, O log value. If that makes any sense. So like, I mean, you can look at an example, like let's say you have 15. 15 is 0, well, 15 is 1111. And you think about that, what's the log of 15? Base 2, that is, base 2. It's about 3.9, so it's approximately 4, and you have 4 bits. So it's log of n, and then when you go to prefix sum, it's also log of n because we're incrementing through the bits. And you know, if we're subtracting the last set bit, or we're adding a last subject, you know, we're either going to go out of range, or we're going to go to 0, and we do this. So yeah, so each time this is O log n plus O log n, which is O log n. So the time complexity for this sum range is O log n. The time complexity for this is O log n. But I mean, this is the prefix sum range is never going to really be called the sum range, so it's going to be called. So this is O log n whenever we call this. It's O log n whenever we call this. And I mean, and this is only called once. So basically, with improvement over the prefix sum array, the prefix sum array was basically going to be O of n every time we update. But now we have O log n. And you know, the thing that sucks is that we do have to add this extra function. But it doesn't make much of a difference, because even if you update and then you recompute the prefix sum, that's like O log n plus O log n. That's still O log n. So it still is a very an improvement over the O n. Yeah, so thank you for watching. Hopefully this is helpful for understanding Fenwick trees and binary index trees. And yeah.